Welcome to the Battery Testing Mentor podcast. My name is Johannes and here we discuss all topics around battery testing, battery handling, battery safety. Every 2 weeks I release a new episode and also send out an email if you want to receive into your inbox what the episode is about, what are the main takeaways. Sign up on www.batterytestingmentor.com. Also, you can reach me on by answering this email or on LinkedIn or these typical channels and let me know your feedback, your ideas, your thoughts. With that, let's go into the interview and continue talking to Pablo Gutierrez Gonzalez about the topic of batteries in eVTOLs and the aircraft industry. It's super interesting, and with that, let's dive in. So, another thing that is also when I worked in this area was also very startling is this extremely high energy densities. Mm-hmm. That, of course, you want to fly, you need energy to fly, and then it's even more important to have as little additional weight as possible. Mm-hmm. So you go to really, really high energy densities.
Yeah.
Which is basically opposing this goal of having it very safe.
Yeah.
Right?
100%.
And then you really need to find the kind of the compromise.
The trade-off,
or
yeah.
What is the way how you would then design for the safety with at the same time having these extreme high energy densities?
Yeah, that's one of the tricky ones. What happens? So to design around thermal runaway, there are not many options. It's a very simple problem that just varies a lot. Yeah. Thermal runaway is one when you see it from first principles. When you kind of simplify it as much as you can, is an object that is going really hot, that in some cases has a lot of debris. Some others you can control, for example, like in cylindrical cells to some extent. And what you want to do is that you want to avoid the next cell to go into critical temperatures, right? Yeah. Which is the temperature at which it will get onset and another thermal runaway. So basically that's it. You have high temperature and you want to avoid that high temperature to make another thing high temperature. The problem gets hard is because all the mechanical induced load that happens around it, right? So this doesn't go just hot. If it was, for example, a glowing thing of uranium or whatever, something really hot, then you're like, okay, that's just chilling there, But this is exploding at the same time, creating a lot of pressure, creating a lot of gas, creating even what we call the ionic atmosphere, right? Because the gas is really hot and the gas has more electrical conductivity than normal air. So what happens is that you create an arc with the chassis just by the gas being hot and being conductive. And then you create another problem, which is a short circuit on top of the thermal runaway, which increases the temperature of all the cells and So I call it more or less the 5/6 design types on how to address that. So the first is that you can hyper isolate. What that means is that you just put so much isolation around that object that the neighbor doesn't get it. Of course, might get heavy. Then you do hyperabsorption, right? That you, instead of avoiding the heat not going through the matter, you just absorb that heat, and then ideally you have body with high heat capacity, which means that absorbs a lot of heat without increasing its own temperature too much. The other thing is dissipate, where you just grab that heat as fast as you can, as good as you can, and just take it somewhere else, right? Which is basically the principle of dissipation, which you can see, for example, the fins in motors and all that thing. That's what they try to do. Yeah. And then the fourth thing is high burst and eject, right? So what you try to do is that you try to make the combustion so violent, so fast that it doesn't have time to remain there and to heat up all the bodies. It just blows and then goes out, right? Of course, it has the drawback that the explosion itself can be aggressively from a mechanical standpoint, but at least thermal-wise, it's not. And the materials, as they increase in temperature, the mechanical properties go down, and so there is some sort of trade-off that one could do there. And the fifth one is my preferred one, is a combination of all of them, right? Which is now that trade-off of all of the previous four is the one that is probably the hardest to find, because it's not the same thing when it comes to, you don't have infinite amount of budget for super fancy materials, right? Not in every case. And you don't have all the space that you would like to do for certain designs to work. So yeah, I think that's more or less how I address the time, the design of the batteries when it comes to thermal runaway, and what I think is possible based on current knowledge.
How do you test for this then? Like when you say, okay, let's make this combination out of all these measures. I mean, typically it doesn't work that you put one combination together, you test it, and then it's fine. So,
I wish
I was a genius.
That would be.
But normally it doesn't work. And how do you find, like, which wheel do you need to turn then? Where do you need to dial up or down?
Yeah, well, I mean, now that I have been involved in this topic and that I have had the opportunity to do so many tests, I think probably I'm a little bit more assertive. Unfortunately, I have to do hundreds and literally hundreds, if not thousands, of tests since the beginning of my career. I think what you could do is first understand the atomic unit, which is the cell, right? You should do a fairly decent testing campaign when it comes to your cell. Understand its dynamics. Thermomechanical dynamics, and maybe even electrothermic mechanical dynamics. And what does that mean? It means like how does it behave under short circuit, right? You normally, it's rather likely that you're gonna have a short circuit, at least for a short amount of time, at the same time that you have a thermal runaway. I mean, unless you have a good design where everything is properly isolated, which is what you're targeting. So you do so this is called the cell characterization test, right? So you basically take, okay, this is the cell, you try to mimic the environment in which it's going to be installed in terms of, the thermal mass around, meaning the heat capacity, the thermal conductivity, and so on, and maybe even the, the heat, I forgot the term, but it's basically the heat that is released when a phase change. The latent heat. Latent heat. So when you do that, you understand, and then you have all of those variables, which is the surrounding of the cell, and then you have the data of the variables that you can input. So, for example, for the MOC3, which is the one specifying how you should test it, you should have combinations of heating rate, heater position, state of charge, aging cycle, and yeah, that's pretty much it. The other variables will be the surroundings and the operation. So the real test, when you do it at the end of the day, has to be done while you're drawing power out of the battery. But no one does the characterization with the power being drawn, which is just way too much work. And it doesn't vary too much. So when you do all of that, you start understanding two things. First, what is the scenario that basically drives the highest amount of battery mass, what we call the glowing mass, right? The mass that has just burned staying there. So what is the amount of residual mass burning that remains there? Because you can have, imagine it's not blowing anymore, it's not spitting fire anymore, but it's like really glowing hot there, just standing, probably sitting next to another cell that is getting super hot as well, right? So, and that induces later on a late thermal runaway, right? So that's why the regulation says that you have to watch it at least for 8 hours, right? And the other outcome is the one that creates the highest thermal flux to the neighbor, right? So it depends on how much mass do you burn, right? So how explosive the event was, which creates certain, let's say, loads in terms of mechanical loads and thermal loads combined. But the other one, so one is mostly mechanical, not too much thermal. The other one is highly thermal, not that much mechanical. So that's more or less what you normally try to look for when you do these characterization tests.
And then you just look how the test was behaving depending on the measures you put in.
Yeah.
And then see, did the measure work or not?
Exactly. And then you just do iteration. So in an ideal world, you should have a really good simulation engineer that understands these physical principles and how these impact the design, and that feed that into the simulation to understand, okay, how is the pressure dealing? How is the pressure, damaging my structure? Which is finally something that people overlook the most. The pressure is a big enemy of the battery design, so you have to kind of take it into account, especially because through the 160 you will have to do explosive atmospheres anyways because of the high hydrogen that's generated prior to the thermal runaway. And then they also put the thermodynamics of the actual mass going into thermal runaway, or how they they become really or let's say all the timeline, right? So it just has a lot of mass, and it's not that not that hot, but then it starts going up in temperature, it goes into thermal runaway, and then ultimately the mass starts disappearing because it's consumed through combustion, and then how all of these dynamics in different locations near to other cells or near to the electronics, how does that play at the final outcome of the design.
Now you mentioned before already like this DO 160G, which is one of these typically aircraft standards. When we look at this kind of now moving from the initial validation where you just have your design and try out, right, and make it work, towards this really certification testing to get this approval for the first flight and so on. What changes there from your perspective? I mean, ideally probably you have everything considered in your validation testing. So you do the certification test and pass it, and just need to do it once, right?
Yeah. Well, I think in the programs where I have been part of, the funny thing is that the thermal runaway and the functional requirements are already so hard to pass that the rest of that part of the design is kind of overlooked, which is a little bit funny because most of the people know that you're going to have a problem, and still you don't design for it, either because there is not enough capacity or because you just simply don't have the skills. But yeah, what happens is that as soon as teams, including myself, probably more in the past than now, but still, finish the design, you know that you're going to fail it most of the times, unless you manage to do something which is, funnily, what I tried to do mostly now is try to reduce the load. Like one of the things that I try to do now is question whether the requirement is properly written, right? I think Elon Musk quite some time ago already had said that there are five principles that you should do to do things right, and the first thing is do the requirements less done, right? And in most of the cases is of course the case that the requirement is already written, right? There are certain standards that you don't want to challenge and tell us, hey, look, I know how to do it better. Yeah, people have been doing this test for not hundreds, but for a couple of decades already, and they have passed it, and there's proof history that they work and they're safe enough and yada yada yada. So you don't want to challenge everything, but you can challenge things in relation to the point of the prototype or the program development stage, so-called TRL, technology readiness level, that you're at. So you can go to the next milestone. You can understand the next problem that is coming without having to try to solve everything the first time. I think probably one of the biggest delays and complications in startups, especially in aviation, is first time right. That is a big enemy. Perfect is the biggest enemy of good enough.
Yeah, just get going and test and try out. And
get familiarized with it,
yeah.
ensure that the people that you have in the team understand not only the system but the standard that you're testing the system against. Sometimes it's good just get people some taste of what they have to, what the real goal is.
Would you say that because these standards and this whole certification in aircraft comes with this old legacy, right, of now 50, 100 years, and has developed in a certain way to make it super safe, right? Is this keeping up with these new developments around eVTOLs, for example? Or is this kind of a standardization scheme that is in some way from the past, and basically for battery-powered flight you would need some different approach?
100%, the second one. I mean, we for sure need a new regulation, and it has been the case. I think EASA, together with a lot of leaders across the aerospace world, specifically in the eVTOL, through this group that I told you earlier, the 112 in the EuroCA, they made a remarkable effort, and I would say to rather good success, in creating standards to define things that are basically filling the gaps across different standards. And in many fields, right? Like, for example, crashworthiness was not good enough. Vibrations is a topic that either is an overkill or an underkill if you follow directly the 160G, just because the way the 160G was defined is it never considered you having 30 engines, where, for example, in the case of Volocopter, having 80 rotors.
On combustion engines.
Combustion engines, right? much less, like probably, I don't know, 6 or so. So in some cases, when you do the calculation, is the amplitudes are wrong, or the frequency spectrum are wrong. So, and for example, for high voltage, we never had batteries as a main source of power in any other aircraft in the past. Probably in a couple of prototypes, but certainly, or at least I'm not aware of in a standard that basically allowed propulsion batteries. I think initially the whole thing was really slow. I think probably because I would say the regulators were at big stake. Probably were the biggest. We're carrying the biggest risk of the whole story, because if you think about it for a minute, what happens is that imagine that you're a regulator, and I'm just following your regulation. So whatever you define to me, I'm just following it. So of course it's my responsibility to be absolutely sure that my product is fail safe. I mean, it's not that because you're the regulator it's your fault, but if I certify against what you have defined as all right or as good, my aircraft ends up falling, you have allowed to use that standard to way more other companies. So it's not only one company failing, but it's the whole industry together. And I think this is something that people at the beginning failed to recognize, how much risk these regulators were handling. And over time, what I noticed is that companies bit by bit realize, okay, we are not against the regulators, or we're not trying to kind of induce the regulators to accept whatever we're putting on the table in terms of design and calculations and whatever, but also to understand that the regulators are playing with us, right? That they are supporting us, like they have ideas on how we can solve it, and which is something particularly funny, because like people often think that regulators might not know your design, or might not be familiar with the technology, or might not know about certain technical advancement. Man, what I have noticed is that they are so goddamn good, but so really good also at politics, that when I have finished sometimes meetings with them and I realize they slapped us, and I think none of my colleagues realized, and we'll have to do our work and then come back to them. So, but yeah, in overall, I think I think now the regulators have done some quite good work. I mean, there is still quite some pending. Yeah, for sure. There are even parts of the eVTOL that are still pending to be written. But I mean, consider the timeline in which they have boosted their delivery of the standards in the last few months, years. I think they're catching up. I think it's really good.
Yeah. Maybe because we are kind of at the end of our time, maybe another big question, like, I mean, the elephant in the room. Now with the situation of Volocopter and Lilium here in Germany, how do you see the future of this? Like, is this now kind of an hiccup where, I mean, two big names were kind of failing, struggling, and the industry will continue to develop and will also continue to grow, and we will fly at one point in time with electrified aircraft, electrified helicopters, electrified small aircrafts? Or is there now some kind of change where then companies say, okay, maybe this eVTOL is not really the approach to go there, but maybe we need to go for maybe larger aircrafts or so? What is your take on this?
Well, I mean, from the technical and commercial point, probably that's topic of a separate or of a new invitation.
Of course, but an aircraft podcast here, electric aircraft.
So, but from the technical point of view, what I would dare to say is, for many years, what I've seen from the aerospace is that whenever we were approaching a battery manufacturer to get some cells to test and to develop our aircrafts, they said, well, the thing is, well, I mean, of course they didn't say it, but the message that we perceived sometimes was, well, you're not big enough for being interesting for us.
Yeah.
And they were mostly focused on getting the automotive to buy more. And at some point, I have the feeling that the bigger players in battery cell technology, they realize, oh, okay, people is buying our cells at our price. I mean, maybe it's okay. Maybe we don't need to make it much better or much cheaper. And then I have the feeling that for a couple of years there was some sort of a stagnation that now we're suffering the consequences of. It is clear that batteries are heavier than combustion, than
petrol.
The petrol, exactly. Yeah. But that doesn't mean that it's going to be the case forever, right? And all things considered, electric engines are much lighter, so it compensates a little bit, not too much, but a little bit. So, and I think, in complementing this initial thought with a TED talk that I saw a couple of days ago. Well, actually a few years, but I resaw it a couple of days ago about a guy that made an analysis of what makes the company success. He found that timing was the most crucial, right? So if you're in an environment where the mass of the batteries and the power density and the energy density is so crucial, and for some other external reason that technology stopped being developed, what happens to this company which relies heavily on this technology to advance, right? So it basically might face some potential winter, right? Yeah. But what I think is that these big players in battery cell technology, they realize, oh damn, we chilled too much on this. We thought we have reached the summit, and now people is buying less and less electric cars. We better boost this now. And recently I saw this video from, I think it's BYD or CATL that I think it was BYD that created this car that can be charged at 10 times the 1 hour charging this charge, but in charging that for me was a game changer. So that means that you can charge faster, that you can refuel your car, right? So for me that is already insane when it comes to power density. And I saw also these other battery technology coming with salt batteries, right? Which apparently are super cheap and are kind of getting rid of all of these other mining going on everywhere else. So in summary, I think that it can be, I mean, I would need to get a little bit more data, but it can be that all of this crisis is woken up the big players in battery cell technology, and I think we're gonna be looking at probably in 1, 2, maybe 3 years, new cell technology that is so much better that companies are starting today in the field of aerospace in electric aerospace, they will be dominating just because of having this good timing.
Yeah, okay. That is definitely something to have our eyes on.
Yeah.
See what will happen in the next couple of years.
100%.
Also, I mean, these high energy densities, high powers for electric aircraft is really a key point. And the more you get into one cell, the longer you can fly.
100%.
Yeah, with that, thank you very much for your time here.
Yeah, no, thank you.
It was great talking to you, and I'm sure we will catch up another time here in the podcast about the next developments. And as you said, there is a lot of things to talk about in this industry.
Absolutely. Thanks for inviting me. And yeah, we had a nice time together.
Yeah, and you, dear listeners and dear watchers, let us know if you have any questions for Pablo. Just reach out to me and I will forward you or put you in contact with him. Have a good time. See you soon.